Welcome to Ask Swagelok. I'm Craig Gifford, here today with Buddy Dam, who's a senior scientist for metallurgy here at Swagelok. And we've been talking about hydrogen embrittlement. And so one of the things we're going to talk about today is how does Swagelok apply our knowledge of hydrogen embrittlement?
It's a really good question. And the first thing I'll say is the hydrogen economy and market is very much evolving.
Oh, yes.
And the research and development going on at national labs and universities around the world and within corporations is very dynamic. There's a lot of new information coming out. So we're trying to stay on top of that. We're staying close to our customers. We've got a lot of successful projects in hydrogen service, and we want to keep learning from that.
Yep.
When we go to try and make material selections, one of the tools we use is something called the relative reduction in area. So if you were to take a material and test it in air, pull it in tension until it fractures,
Okay.
you can measure the ductility as a reduction in area. If you repeat that test in the hydrogen environment, you'll get a lower reduction in area.
Okay.
And that relative difference between in hydrogen and air can be expressed as a percentage.
Okay.
Right? So if you were to test, and I'll say austenitic stainless steels are one of the more common capable alloys in hydrogen service. But if you were to test 304 stainless, you would get about a 50% relative reduction in area.
Okay.
If you take 316L off the shelf, you'll get around a 80%.
Oh.
So it's much better.
Okay.
Now, Swagelok, we use an enhanced 316L with a little bit more alloy, and that will give you a 90% relative reduction in area. Right? Now, some other things that are important are things like welding. Right? So a lot of our customers weld tubes together, or they'll weld tubes to our components.
Yep.
So we want to understand how that weld performs. When we test the weld in hydrogen, we get around an 85% relative reduction in area compared to 90. And so that's not
Still
much.
good.
Yeah, really good. Another area of concern is strain hardened. So we strain harden 316 stainless steel or cold work it in order to increase its strength. And we do that so that we can contain more pressure.
Okay.
Pressure containment in hydrogen can be on the order of 700 bars or 10,000 PSI. And so when we tested our product cold hardened, we got an 85% relative reduction in area versus a 90, so really good. But of course, in a real component, we're not designing till we load till fracture, right? Instead, what happens is cyclic pressure cycles or external cyclic loading results in accumulated damage through fatigue. And so it's important to understand how does fatigue get affected by hydrogen. So if you test 304 stainless steel and compare its performance in air and in hydrogen, you lose about 90% of its fatigue cycle life.
Okay.
If you test 316L and 316L with a slightly better alloy content, you get about a 70% loss in cycle life. So that's still significant.
But a big difference.
It's a big difference. Yeah. And if you make good design choices to manage the stresses, then you can reduce that. So for example, a modest reduction in stress can give you a 10-fold increase in cycle life.
Okay.
So it can really be a game changer.
Well, that's great.
Yeah.
Well, thank you, Buddy. And thank you for joining us for Ask Swagelok.